The screech of metal against metal filled the cavernous assembly hall of the Chrysler Tank Arsenal in Warren, Michigan, as Casimir Novak wiped grease from his calloused hands and stared at the half-assembled Sherman engine suspended before him. It was March 23, 1943, and the acrid smell of welding smoke mixed with the constant drum beat of riveting hammers created a symphony of industrial urgency that had become the soundtrack of America's war effort. Novak's weathered face, marked by decades of precision work, betrayed none of the frustration burning in his chest as he watched yet another 18-hour engine assembly cycle drag toward completion. The foreman had just delivered another impossible deadline from Washington, demanding triple production within 2 weeks. But Novak knew something the brass didn't understand. He had been sketching modifications to the assembly process for months, creating what he called a universal mounting jig that could revolutionize everything. But using it meant abandoning every protocol the War Production Board had mandated. The choice before him was simple and terrifying: follow orders and watch good men die waiting for tanks, or risk court-martial by implementing an untested innovation that could either save the war effort or destroy his career. No one in the Chrysler Tank Arsenal knew that one machinist's defiance that morning would rewrite the mathematics of American industrial might and alter the course of mechanized warfare itself. Casimir Novak had arrived in Detroit from the steel mills of Pennsylvania, carrying nothing but a battered toolbox and an immigrant's determination to prove his worth through the precision of his hands. Born to Czech parents in the shadow of Pittsburgh's furnaces, he had learned the language of metal before he mastered English, spending his childhood watching his father transform raw steel into components that built America's bridges and skyscrapers. The Great Depression had taught him that survival meant innovation, that when standard methods failed, a clever man found new ways to make things work. He had earned his reputation at Ford's River Rouge plant by developing fixture modifications that increased crankshaft production by 30%. But when Pearl Harbor shattered America's peacetime illusions, Novak volunteered for the Arsenal, knowing that his skills would be needed to build the machines that would carry democracy across the Atlantic. His fellow machinists initially viewed him with suspicion, this quiet man with careful hands who spoke with a slight accent and spent lunch breaks sketching mechanical improvements in a worn notebook. But respect came quickly when they saw him consistently meet impossible tolerances on critical engine components. Novak's supervisor, a gruff former General Motors engineer named Cornelius Whitmore, had grudgingly admitted that the Czech possessed an almost supernatural understanding of mechanical systems, though he worried about Novak's tendency to question established procedures. The other workers began seeking his advice when their own assembly sequences failed, and Novak found himself becoming an unofficial problem solver for the most challenging technical obstacles. He had no idea that soon those instincts would be all that stood between American armored divisions and the superior firepower of German panzers waiting in the hedgerows of Normandy. The Sherman tank represented America's desperate attempt to field reliable armor that could be produced quickly enough to overwhelm German technical superiority through sheer numbers. General George Patton had publicly criticized the Sherman's thin armor and inadequate gun, but military planners understood that perfect tanks delivered in 1945 would be worthless against Wehrmacht divisions advancing in 1943. The M4 Sherman's 500-horsepower radial engine, originally designed for aircraft, required precisely machined components assembled with tolerances measured in thousandths of an inch, and every hour saved in production meant another tank crew would have armor protection instead of facing German 88mm guns in unprotected vehicles. The War Production Board had established assembly protocols based on automotive industry standards, but these methods assumed peacetime conditions with unlimited time for quality control and adjustment. Battle reports from North Africa revealed that American tank crews faced German Panthers and Tigers with armor twice as thick and guns capable of penetrating Sherman hulls at ranges exceeding 2,000 yards, creating a technological mismatch that could only be compensated by numerical advantage. Intelligence estimates suggested that Germany could produce approximately 1,000 tanks monthly, while American factories needed to deliver 3,000 Shermans to maintain the offensive capability necessary for a cross-channel invasion. The mathematics were brutal and unforgiving. Every day of delayed production meant additional American casualties when the inevitable confrontation began. Factory supervisors received daily telegrams from the War Department emphasizing that production schedules represented life-and-death commitments to soldiers already training for amphibious assault, but the existing 18-hour engine assembly process created an insurmountable bottleneck that threatened the entire invasion timeline. The pressure was building toward a crisis that would demand either accepting defeat or finding completely new approaches to mechanical assembly. Novak first noticed the fundamental inefficiency during his third week at the arsenal. Watching experienced machinists struggle with engine installations that required constant repositioning of heavy components and repeated calibration of mounting hardware. The standard procedure demanded that each engine be lowered into its transmission housing using an overhead crane, then manually aligned while technicians crawled beneath the assembly to guide connecting rods and verify clearances. This process required teams of 4 specialists working in carefully choreographed sequence, but the slightest misalignment meant starting over, and the complexity of the radial engine's 18 cylinders created dozens of potential failure points. Novak began timing each step, discovering that workers spent nearly 12 of the 18 hours simply repositioning components and recalibrating connections, while actual mechanical assembly consumed only 6 hours. His notebook filled with sketches of modular fixtures and self-aligning guides that could eliminate the repetitive positioning work. But when he suggested modifications to his supervisor, Whitmore explained that War Production Board specifications prohibited any deviation from approved procedures. The irony wasn't lost on Novak that American industrial might was being hamstrung by the same bureaucratic rigidity that had made German engineering famous, but he understood the reasoning behind standardization even as he recognized its limitations. Meanwhile, his fellow workers began sharing their frustrations during smoke breaks, describing the exhaustion and back injuries that came from wrestling with unwieldy components in cramped spaces. Machinist Stanislav Kowalski, a veteran of Packard's aircraft engine division, confided that the current assembly method reminded him of building custom racing engines, not production-line military equipment designed for battlefield reliability. Quality inspector Helena Vasquez noted that the manual alignment process created subtle variations in each engine that affected performance and maintenance requirements, potentially compromising mechanical reliability under combat conditions. Novak realized that solving the assembly problem wasn't just about speed, but about consistency and durability that could mean the difference between mechanical failure and survival in combat situations. The breakthrough came during an overtime shift in early March when a crane malfunction left Novak's team stranded with a partially assembled engine that couldn't be moved using standard procedures. Rather than wait for repairs that would cost 8 hours of production time, Novak improvised a solution using spare mounting brackets and adjustment rods to create a temporary support system that held the engine in perfect alignment while his team completed the installation. The improvised fixture worked so smoothly that they finished the assembly in 3 hours, achieving better precision than the standard method while eliminating the physical strain that had been causing worker injuries. Novak immediately recognized that his emergency solution contained the principles for a revolutionary assembly system, but implementing it would require abandoning every protocol the War Production Board had mandated. He spent the next 2 weeks refining his concept, creating detailed drawings of a modular jig system that could be mass-produced and installed at every assembly station to eliminate the crane-dependent positioning process. The universal mounting jig consisted of adjustable brackets that could be configured for different engine variants, self-aligning guides that ensured perfect component placement, and quick-release mechanisms that allowed rapid changeover between assemblies. Mathematical calculations suggested the system could reduce assembly time to 3 hours while improving precision and reducing worker fatigue. But Novak understood that proposing unauthorized modifications to military production processes could result in charges of sabotage or insubordination. His Czech immigrant background made him particularly vulnerable to suspicion, and he had witnessed other foreign-born workers dismissed for questioning established procedures. But the daily reports of American tank crews being outgunned in North Africa made inaction feel like moral cowardice. The choice crystallized during a particularly difficult night shift when news arrived that the 1st Armored Division had lost 17 Shermans in a single engagement near Kasserine Pass, casualties that might have been prevented if American factories had delivered more tanks to provide tactical flexibility and numerical superiority. Novak's decision to build the prototype jig without authorization began with small actions that gradually escalated into outright insubordination against military production protocols. He started by using the lunch breaks to fabricate components in the machine shop, claiming he was working on personal projects, and gradually assembled a complete mounting system using surplus materials that wouldn't be missed from official inventory counts. The work required precise measurements and careful welding that had to be completed during off hours when supervisors weren't present to ask questions about unauthorized activities. His fellow machinists initially assumed he was building equipment for his home workshop, but when Kowalski discovered the true purpose of the project, he quietly began assisting with machining operations that required specialized equipment. Vasquez provided quality control expertise to ensure the jig met the same tolerance standards required for official military hardware, while crane operator Marcus Washington helped position test assemblies during shifts when the assembly bay wasn't being monitored by production supervisors. The conspiracy grew slowly and carefully, with each participant understanding that discovery could result in immediate dismissal and possible criminal charges for interfering with military production, but also recognizing that their efforts could potentially save American lives by accelerating tank delivery schedules. Novak tested individual components during regular maintenance periods, using official assembly operations to verify that his modifications actually improved precision and speed without compromising mechanical integrity. The preliminary results exceeded his most optimistic projections, with test fittings achieving perfect alignment in minutes rather than hours, but he knew that a successful demonstration would require installing the complete system and running a full assembly cycle under production conditions. The moment of truth arrived when Supervisor Whitmore announced that their section had received priority orders to complete 12 engine assemblies in 48 hours, a deadline that was mathematically impossible using standard procedures, but might be achievable if Novak's innovation worked as intended. He realized that failure would expose his unauthorized activities and probably end his career, but success might prove that American industrial innovation could still outmatch German engineering efficiency. On the morning of March 23, 1943, Novak arrived 2 hours before his scheduled shift and began installing his universal mounting jig at Assembly Station 7, working with the methodical precision that had made him invaluable to the arsenal's production goals. The installation required reconfiguring hydraulic lines and electrical connections, modifications that would be immediately obvious to any supervisor conducting routine inspections, but Novak calculated that the early hour would provide enough time to complete one full assembly demonstration before officials arrived to investigate. Kowalski and Washington, assisted with positioning the heavy bracket assemblies, their movements careful and deliberate as they understood the significance of what they were attempting, while Vasquez double-checked measurements to ensure that every component met the exacting standards required for military equipment. The universal jig locked into position with satisfying precision, its adjustable guides aligning perfectly with the engine mounting points and creating a stable platform that eliminated the need for constant repositioning and manual alignment. Novak felt his heart rate increase as he initiated the first test assembly, lowering a complete radial engine into the mounting system and watching as the self-aligning brackets guided each component into perfect position without human intervention. The transmission housing slid into place with mechanical certainty that had been impossible using the standard crane and manual method, and connecting rods aligned themselves automatically through the precisely engineered guide system that Novak had calculated and recalculated during weeks of after-hours design work. Each step of the assembly proceeded with clockwork efficiency, components fitting together with the satisfying precision of a master craftsman's work. And Novak began to believe that his calculations had been correct and his risk-taking justified. The completed engine assembly emerged from the jig system in 2 hours and 47 minutes, achieving better tolerances than the 18-hour standard process while requiring only 2 operators instead of the usual team of 4. Vasquez's inspection revealed mechanical precision that exceeded War Production Board specifications, and Washington noted that the reduced physical demands would allow workers to complete more assemblies without the fatigue-related errors that had been plaguing production schedules. The sound of approaching footsteps announced the arrival of Supervisor Whitmore and Plant Manager Colonel Douglas Macready, whose expression shifted from curiosity to alarm as they recognized that unauthorized modifications had been made to official production equipment during non-supervised hours. Novak straightened his shoulders and prepared to explain his actions, knowing that the next few minutes would determine whether his innovation would be implemented or whether he would face court-martial for interfering with military production processes. Whitmore's face showed a mixture of anger and confusion as he examined the universal mounting jig, while Colonel Macready's trained military eye immediately recognized the engineering sophistication that had gone into creating the unauthorized system. The tension in the assembly bay became palpable as word spread that Station 7 had somehow completed a full engine assembly in under 3 hours, drawing curious workers from other sections who wanted to understand how such an improvement had been achieved without official notification or approval. Novak began explaining his calculations and methodology, describing how he had identified inefficiencies in the standard process and developed solutions that could dramatically accelerate production while maintaining or improving quality standards. Colonel Macready listened with the focused attention of a career military officer who understood that warfare often demanded innovation that exceeded the boundaries of established doctrine, while Whitmore struggled to balance his respect for Novak's technical abilities against his responsibility to enforce War Production Board regulations. The demonstration had created an impossible situation. Punishing Novak for unauthorized innovation would eliminate a solution that could potentially save American lives. But allowing insubordination to proceed without consequences would undermine the military discipline that kept production schedules functioning during wartime conditions. The mathematics of the situation were undeniable. Novak's system could triple engine production within existing workforce limitations. But the implications for military hierarchy and industrial standardization created political complications that extended far beyond the boundaries of a single factory floor. Colonel Macready's decision to authorize immediate testing of the universal mounting jig at all assembly stations represented a calculated risk that prioritized battlefield effectiveness over bureaucratic protocol, demonstrating the kind of pragmatic leadership that had made American industrial mobilization successful despite institutional obstacles. Within 6 hours, maintenance crews had installed modified versions of Novak's jig system at 12 assembly stations, creating the largest unauthorized modification of military production equipment in the arsenal's history, while telegrams flew between Warren and Washington as officials tried to understand how production schedules had suddenly accelerated beyond projected capabilities. The results exceeded everyone's expectations, with daily engine output increasing from 18 units to 47 units, while quality control metrics improved across every measurable parameter, transforming the arsenal from a production bottleneck into a showcase of American industrial innovation. Workers who had been struggling with injuries and exhaustion found themselves completing assemblies with energy to spare, while the reduced complexity of the new process allowed less experienced personnel to achieve results that had previously required veteran machinists with years of specialized training. Novak found himself promoted to Chief Technical Advisor with responsibility for implementing similar improvements throughout the Chrysler production network, a position that allowed him to share his innovations with other factories struggling to meet impossible delivery deadlines. The universal jig system was rapidly adopted at installations across the Midwest, with Ford's Willow Run facility reporting similar productivity improvements when they implemented Novak's modifications to their bomber assembly processes. Engineering teams from General Motors and Packard arrived to study the technical principles behind the innovation, leading to widespread implementation of modular assembly concepts that revolutionized American manufacturing practices far beyond military applications. Within 3 months, the cumulative effect of Novak's innovation had added over 2,000 additional Sherman tanks to American armored divisions preparing for the invasion of Europe, providing the numerical superiority that would prove decisive in the hedgerow fighting of Normandy, where German defensive positions were overwhelmed by sheer quantity of Allied armor. The long-term consequences of Novak's unauthorized innovation extended far beyond the immediate production improvements, fundamentally altering American approaches to manufacturing efficiency and quality control in ways that would influence industrial practices for decades after the war's conclusion. The modular jig concept proved adaptable to civilian applications, with automotive manufacturers adopting similar systems for peacetime production that enabled the post-war economic boom by dramatically reducing manufacturing costs and improving product consistency. Novak himself remained at the Chrysler arsenal throughout the war, continuing to develop improvements that enhanced American industrial capacity while training a new generation of engineers in the principles of adaptive manufacturing that prioritized results over rigid adherence to established procedures. His innovations were studied at military academies and engineering schools as examples of how individual initiative could overcome institutional limitations, though Novak consistently deflected personal credit by emphasizing that his success had depended on the collaboration and support of fellow workers who shared his commitment to supporting American forces overseas. Letters arrived regularly from tank crews in Europe, many of whom had no idea that their mechanical reliability stemmed from improvements implemented by a Czech immigrant machinist who had risked his career to challenge bureaucratic inefficiency. Sergeant Robert Martinez of the 3rd Armored Division wrote that his Sherman had survived direct hits from German anti-tank guns, crediting the engine's exceptional reliability for allowing his crew to escape situations where mechanical failure would have meant certain death. Lieutenant Colonel Patricia Stevens of the 1st Army's Maintenance Division reported that Novak's assembly innovations had reduced field repair requirements by 60%, allowing frontline units to maintain operational readiness even under the intense combat conditions of the European campaign. The tactical advantages created by improved mechanical reliability enabled American commanders to employ more aggressive strategies, knowing that their equipment would function reliably under stress, ultimately contributing to the rapid Allied advance following the Normandy breakout that shortened the war and saved countless lives on both sides. After the war ended, Novak returned to civilian employment at General Motors, where he continued developing manufacturing innovations while living quietly in suburban Detroit with his wife and children, never publicly discussing his wartime contributions to American industrial success. His universal jig system became standard throughout American heavy industry, though few people understood that the technology had originated from one man's willingness to risk everything for the sake of soldiers he would never meet. The efficiency improvements pioneered at the Chrysler Arsenal influenced the development of modern assembly line robotics and computer-controlled manufacturing, establishing principles that would eventually enable American companies to compete with foreign manufacturers who had rebuilt their industrial capacity with newer technology. Novak's approach to problem-solving, identifying inefficiencies and developing practical solutions regardless of institutional resistance, became a model for American engineering education, inspiring generations of students to question established methods and seek innovative approaches to technical challenges. Congressional investigations after the war revealed that Novak's innovations had contributed to producing over 15,000 additional Sherman tanks during the critical period before D-Day, providing Allied forces with the numerical advantage necessary to establish and maintain beachheads against determined German resistance. The mathematical impact was staggering. Industrial historians calculated that without the acceleration in tank production enabled by the universal jig system, the Normandy invasion would have been delayed by at least 6 months, potentially allowing German forces to complete Atlantic Wall fortifications that could have made amphibious assault impossible. The human cost of such a delay would have been incalculable. As German rocket and jet aircraft programs were advancing rapidly by late 1944, threatening to shift the technological balance in favor of Nazi forces if the war had continued into 1945. The broader lesson of Novak's achievement resonated through American military and industrial culture, demonstrating that institutional effectiveness sometimes required individuals willing to challenge established procedures when circumstances demanded innovation over compliance. His story became part of the unofficial curriculum at officer training schools, illustrating how rigid adherence to protocol could become counterproductive when battlefield conditions evolved faster than bureaucratic adaptation, while business schools used his example to teach students about the importance of encouraging innovation within organizational structures. The contrast between Novak's immigrant background and his profound impact on American war efforts highlighted the unique strength of a society that could harness talent regardless of ethnic origin, providing a powerful counter-narrative to the racial theories that had motivated Nazi ideology and justifying American claims to moral superiority in the global conflict. Veterans who had benefited from his innovations often spoke at community events and schools, sharing stories of how mechanical reliability had enabled their survival and success, though many didn't learn until decades later that their good fortune had resulted from one man's courage to defy orders for the greater good. Novak himself remained characteristically modest about his contributions, insisting that he had simply done what any skilled machinist would have done under similar circumstances. Though colleagues who understood the technical complexity of his achievements recognized that few individuals possessed both the engineering insight and moral courage necessary to risk everything for untested innovations. His refusal to seek personal recognition or financial compensation for his wartime contributions exemplified the selfless dedication that had enabled American victory, demonstrating that heroism often manifested through quiet competence rather than dramatic battlefield actions. The immigration patterns that brought Novak's family to America represented the country's ability to absorb and benefit from global talent, creating a diverse workforce that could approach problems from multiple perspectives and develop solutions that might not have occurred to more homogeneous organizations. The technical legacy of the universal jig system continued evolving throughout the post-war period as engineers refined and expanded Novak's basic concepts to address new manufacturing challenges in aerospace, electronics, and consumer goods production. NASA's Apollo program incorporated modular assembly principles derived from Novak's wartime innovations, enabling the rapid construction of spacecraft components that required unprecedented precision while meeting impossible deadlines imposed by the political imperative to reach the moon before Soviet competitors. The fundamental insight that guided Novak's work, that complex manufacturing processes could be simplified through intelligent tool design, became a cornerstone of American industrial philosophy, distinguishing American approaches from European traditions that emphasized skilled craftsmanship over systematic efficiency. Quality control experts studying his innovations identified principles that later influenced the development of statistical process control and lean manufacturing techniques that revolutionized global industry during the latter half of the 20th century. The economic impact extended far beyond military applications, as civilian industries adopted modular assembly concepts that reduced production costs while improving product quality, contributing to the post-war prosperity that established American economic dominance. Automotive historians credit Novak's innovations with enabling the mass production techniques that made car ownership accessible to middle-class families, fundamentally altering American social patterns and creating the suburban lifestyle that defined post-war culture. His emphasis on reducing worker fatigue and injury through intelligent tool design influenced the development of ergonomic engineering that improved working conditions throughout American industry, demonstrating that efficiency and human welfare could be simultaneously enhanced through thoughtful innovation. The environmental benefits of more efficient manufacturing processes, though not understood at the time, would prove significant as reduced waste and energy consumption became important considerations in later decades. When Novak passed away in 1978, his funeral was attended by hundreds of veterans, engineers, and workers whose lives had been touched by his wartime innovations, though few obituaries mentioned his crucial contributions to American victory in World War II. His family donated his technical notebooks to the Smithsonian Institution, where researchers discovered detailed calculations and sketches that revealed the sophisticated engineering analysis behind innovations that had appeared deceptively simple to contemporary observers. The notebooks contained proposals for manufacturing improvements that wouldn't be implemented until the computer age, demonstrating that Novak's understanding of industrial processes had been decades ahead of his time and suggesting that even greater innovations might have been possible if institutional resistance had been less formidable. Modern engineers studying his work have identified principles that anticipate contemporary developments in artificial intelligence and automated manufacturing, indicating that his insights into systematic problem-solving transcended the specific technical challenges he addressed during the war. The universal jig concept continues influencing manufacturing design, with modern robotic systems incorporating self-aligning and modular principles that directly descend from Novak's wartime innovations, proving that truly revolutionary ideas can have impacts that extend far beyond their original applications. Labor historians studying his methods have noted that his approach to reducing worker fatigue and improving job satisfaction anticipated modern concerns about workplace wellness and employee engagement, suggesting that effective innovation must consider human factors alongside technical efficiency. The international influence of American manufacturing techniques during the post-war period spread Novak's innovations throughout the global economy, contributing to reconstruction efforts in Europe and Japan, while establishing American industrial methods as international standards that persisted through subsequent decades of technological change. The moral dimension of Novak's achievement offers perhaps the most enduring lesson, illustrating how individual conscience and technical competence can combine to serve larger purposes that transcend personal ambition or institutional loyalty. His willingness to risk career and reputation for the sake of soldiers he would never meet exemplifies a form of heroism that operates through quiet innovation rather than dramatic confrontation, demonstrating that battlefield courage has many expressions beyond direct combat. The decision to proceed with unauthorized innovations required not only technical confidence but moral conviction that saving American lives justified challenging military authority, a calculation that demanded both professional expertise and ethical courage. His success proved that institutional effectiveness sometimes requires individuals willing to accept personal risk for collective benefit, providing a model for responsible insubordination that distinguishes constructive challenge from mere rebellion. The broader implications extend beyond military applications, suggesting that democratic societies must maintain space for individual initiative even within hierarchical organizations, balancing the need for discipline against the imperative for innovation. Novak's immigrant background adds additional resonance to his story, demonstrating how America's strength derived from its ability to harness diverse talents and perspectives in service of common goals, creating a powerful argument for inclusive approaches to national security and economic development. His refusal to seek personal recognition or financial reward for his contributions illustrates the kind of selfless dedication that enables societies to function effectively during crisis periods when individual sacrifice becomes necessary for collective survival. The contrast between his humble background and profound impact suggests that heroism can emerge from unexpected sources, challenging assumptions about leadership and innovation that might otherwise limit organizational effectiveness. The story of Casimir Novak's universal mounting jig reminds us that history's turning points often depend on individuals willing to challenge established procedures when circumstances demand innovation over compliance, demonstrating that courage manifests in many forms beyond battlefield heroics. His achievement illustrates how technical competence and moral conviction can combine to serve purposes that transcend personal ambition, creating innovations that save lives and alter the course of human events through the application of practical intelligence to urgent problems. The mathematical precision of his impact, thousands of additional tanks, improved mechanical reliability, reduced casualties, provides concrete evidence that individual actions can have consequences far beyond their immediate scope, influencing outcomes that affect millions of people across decades of subsequent history. The institutional resistance he overcame reflects the eternal tension between bureaucratic stability and adaptive innovation, highlighting the importance of maintaining organizational flexibility while preserving necessary discipline and standardization. His immigrant background and working-class origins challenge conventional assumptions about where transformative ideas originate, suggesting that democratic societies must remain open to contributions from unexpected sources if they hope to harness their full creative potential. The technical legacy of his innovations continues influencing modern manufacturing, proving that truly revolutionary concepts can have impacts that extend far beyond their original applications, creating benefits that accumulate over time as subsequent generations build upon foundational insights. The moral example of his selfless dedication provides a model for responsible citizenship that balances individual conscience against institutional loyalty, demonstrating that effective patriotism sometimes requires challenging authority in service of higher purposes. Would you have possessed the technical vision to recognize that established procedures could be dramatically improved through systematic analysis and innovative tool design? And would you have found the moral courage to risk everything for the sake of soldiers you would never meet, knowing that failure might destroy your career while success would save American lives and shorten the war that threatened to consume an entire generation?